Hello, grade 11s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Abutiwa Sos Ugobela Maths. And without any further ado, let's look at these questions that we have here. Okay, so we have question 3 still on electrostatics. It says a sphere Q1 with a charge of negative 2.5 microcoulomb is placed 1 meter away from a second sphere Q2 with a charge of positive 6 microcoulomb. So we already know what to do here. We should convert these ones to coulombs by multiplying by 10 to the exponent of negative 6. But then our distance is in the desired SI unit. The spheres lie along a straight line as shown in the diagram below. Point P is located at a distance of 0.3 meter to the left of sphere Q1, as we can see here. The diagram is not drawn to scale. Then 3.1 says define the term electric field at a point. We mainly just say electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. So for 2 marks, that's how you are supposed to define electric field at a point according to your CAPS document. Then 3.2 says draw the resultant electric field pattern for the two spheres, right? Now we can see that the two spheres here are negative. We have a negative one meant to say, and then another one is positive. So they are unlike charges, right? Now note that they do not say after contact or anything. They just said draw the resultant electric field pattern for the two spheres that we are looking at, the Q1 and Q2, as they are. So this one is negative and then this one is positive. Now for this one we can draw an attraction, right? An attraction of the charges. Now how do we indicate that? You only need a few fill lines, guys. You do not need to flood your book with fill lines, because the more fill lines you put in there, you risk the chance of having to have them to actually touch, which is what we don't want, right? We don't want your fill lines to ever touch, right? Then that's how you indicate those ones. That's how you indicate those. Then let's just try to fill in another one there, just so that it bends, somehow bends like that. So that it bends somehow like that, bends like that. So now I should be careful that they do not touch and then they all come from their individual points, right? Now, if this is a negative, this is a positive, we know that the charges are inward for the negative, inward, but then the charges are what? Are outward in reference to the positive charge. So they are outward. So facing outward. And then that's how you should indicate that. So outward for the positive ones and then inward for the negative ones. Now we should make sure they do not touch, they do not cross, right? And then the direction of the fill lines is also correct and the shape is correct, right? So 3 marks for that. Then 3.3 says calculate the net electric field at point P due to the two charge spheres Q1 and Q3. So, okay, let's go ahead with that one. So to calculate that one, we know that the net electric field at point P is always in reference to that point charge. So that means we take Q1 in reference to that P and then Q2 in reference to that P. So always the electric field is in reference to the positive point charge. Remember, this is a positive point charge. So the first thing that we need to indicate is the direction of P due to these two charges, right? So if this is positive, but Q1 is negative, where will P go? Will it be attracted to Q1 or repelled from Q1? Now we know that unlike charges attract. So that means it will be attracted towards Q1. So this will be the electric field of P due to Q1. But then since it is positive and your Q2 is also positive, that means we will experience a repulsion force from Q2, making the direction of point P to the left. So this is electric field of P due to Q2. Now you do understand that the distance is small because the electric field, the magnitude of the electric field is small because the distance in between them is great, right? So remember, this vector here is indicating that strength of the electric field. So the strength is small because the distance in between them is greater, but then here the strength is bigger because the distance in between them is small, right? So there's that inverse relationship between electric field and the distance. So even if you are looking at it in terms of the formula, KQ and then R squared here. So if you are looking at it in terms of the formula, you can see that the bigger the distance, the smaller the electric field. Okay, so now let's calculate. Starting with this one, this would be EP due to Q1. So we're going to take that one as our E1. And then this is E is equals to KQ over R squared. So let's use Q1. So that's 9 times 10 to the exponent of 9. Our Q1 is 2.5 times 10 to the exponent of negative 6. Remember, I do not substitute that negative here. And then the distance in between, it's 0.3. It's in the desired SI unit. So I'm just going to substitute it exactly as it is. Then if you punch all that into your calculator, you get 250,000 Newton per Coulomb, right? But then now to calculate the electric field strength of P due to Q2, which is, we're going to take this one as our E2. This is what we're going to do. Again, the formula E is equals to K Q2 this time over R squared. And then if we substitute here, that's 9 times 10 to the exponent of 9. Our Q2 is 6 times 10 to the exponent of negative 6 over the distance in between them. It's only 1 meter, 1.3 meter meant to say, the distance between point P. So remember, it's in reference to point P. So this is our Q2, but then in reference to point P, it's 1 meter and 0.3, which should be 1.3 meters. Excuse me for that. Then our E, our electric field now, when we punch all that into our calculator, it's supposed to give us 31,952 0.66, right? So let's just round that one to 2 decimal places. So Newton per Coulomb. Now you see that it confirms the fact that because the distance in between these ones is greater, then it will end up with a smaller electric field. But then here the distance in between them was smaller, then that's why it had a bigger electric field. Right. Okay, so now to calculate our E net, this is what we do. So if this one, we say it is going to the right, and then this one here, it's going to the left, then this one, if we're taking right as positive, it should be positive and left as negative. Then this is E net is equals to E1 plus E2. Our E1 is positive 250,000, but our E2 is now negative because it's going to the left, 31,952.66. And then punching that into your calculator, you get 218,047.34 Newton per Coulomb. To which direction? Because it's positive, that means it's going to the right. Now you can even see it in terms of your vector diagram. Remember, it will end up going to the direction of the bigger vector. So the bigger vector is the one which is on the right. So hence your E net will be to the right. And that's how you were supposed to tackle this question for 5 marks. And then let's see the mark allocation. Where did they allocate the marks? So obviously we had a mark for the formula. We had a mark for substitution, but then they no longer mark the formula for the second one. They just mark here. And then they mark having to subtract these ones. And then they mark having to conclude and also have the right direction, right? So the correct direction there, along with the correct FNet. So that's supposed to be 5 marks. Okay, so we have came to the end of the lesson. That's how you were supposed to tackle this question for a total of 10 marks. And please press the thumbs up button if you have enjoyed the lesson and then you have found it helpful. And if you've been watching the videos and haven't subscribed yet, please press that subscribe button. And if you are watching from Facebook, please like and follow the page. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.